So thank you, Edouard, for attending this seminary. And so you are very welcome. It was a pleasure for me to meet you in Japan some few years ago, and it's a pleasure again to welcome you in Sergi. So it will be very interesting for us from your techniques and also from the thematics that you consider to know a bit more about your work. Thank you very much.
Hello. Okay, now it should be good. Yes. Okay. Hello, everyone. Thank you, Paul, for this warm welcome. So it's my pleasure to be here today. I know it's a bit weird if I speak English, because maybe most of us speak French here, or maybe all of us, but I'm not used to make presentation in French anyway. And I mean, I think maybe for the future, since this is being recorded, it's interesting to also non-French speaking people. So yeah, my name is Edouard Fouché. I'm postdoc at the Karlsruhe Institute of Technology, and this presentation is about automated decision-making for sustainable energy systems. So this is not a presentation about one specific work of mine, and I'm not going to go in much detail in any specific place, but rather I would say this is a holistic view on the research topics that are of interest to me and that I see myself pursuing for the next few years. And I will also speak a little bit about my work in that respect. So yeah, as Paul said, I'm a computer scientist, and I know that we computer scientists and mathematicians tend to focus a little bit on different aspects. Nonetheless, I hope that this presentation will be interesting, and that maybe this sparks interesting discussions for like future collaboration, etc. So, okay, I'm just starting my timer so that I keep the time. So this is my short outline for today. So I will start by talking a little bit about the challenges that arise when we consider the energy systems that we're going to have to use in the future. Then I will introduce, and I think it will be clear why those energy systems will require very efficient and effective, so automated decisions. But I will also say that it's really hard when you consider the characteristics of the real world. And that's where I would bring like my research vision that yeah, I see myself getting busy with for the next few years. I talk a little bit about my previous work, and then I will conclude. Okay, so we are definitely living a massive paradigm shift. First of all, in terms of supply, so we massively need to change the way we produce energy. So far, nuclear energy or coal or yeah, burning gas, which is definitely like messing up the planet. Okay, nuclear energy is still controversial, especially okay in France. We don't know really like what the politics are going to decide for the next few years, but at least where I live in Germany, it's pretty clear that in the future we need instead to produce much more of our energy from renewable sources, and there, in particular, we're talking about wind and photovoltaic energy. So this brings challenges because this type of energy generation is time dependent. The sun doesn't shine every day and doesn't shine for the same amount of time every day, and also the wind production is quite say volatile, and also because we are producing the energy from power electronics instead of rotating machinery, it is much harder to maintain a stable frequency in the grid at any time, which we need to guarantee stable supply for everyone. And the paradigm is not only changing from the point of view of the supply, but also from the demand. So I think also in Germany, I think the goal is that by 2030, we will not sell any like thermic cars, but only electrical cars. So at like, let's say, yeah, small time horizon, we can expect pretty much almost everyone will drive electric cars. And those electric cars need to be charged. Also, there are more and more households who now have like private, say, solar panels. And this really changed the way we are in the end consuming energy. Because those electric cars, they require, like if you want to charge them fast, they require a lot of power. And obviously, if everyone decides to charge their electric cars at the same time, for many of the existing, say, architecture of the grid, it's not possible. And also the behavior is different, because now the consumer also produce their own energy because of those electric panels. And they can make different choices, like, okay, use this energy, for example, to charge their electric cars, or maybe they want to charge some battery, or maybe they want to sell this energy that they produce to the grid. And because of those two changes in terms of supply and demand, the control of future grids is going to be one of the, I would say, major challenge of the 21st century. So there is some, some discussion among electrical engineers, so how we should design a future energy system, and it's likely that a future energy system will be much more decentralized. So this is the opinion that you hear when you talk mostly with like electrical engineers. So we are moving from the microgrid, which is one centralized networks that distribute energy to everyone, to instead of a network of so-called microgrids, which are then decentralized grids. So here is a small, you can see on this slide, a small graphics that I try to represent this. So the microgrid in the middle basically interconnects local green energy sources, different storage technologies, which can be not only batteries, but you can think of like storing energy in the form of heat, or mechanical energy storage, or even gas, and with the local households and industry. And the microgrid can decide at any time to be connected to the microgrid, so those conventional energy production means, or to connect to other microgrids and trade energies on those different energy layers. So we're talking about energy layers because energy in the future is mostly not going to be only electricity. It's also going to be maybe hydrogen or heat or mechanical storage. And so the goal when one operates those microgrids is that you wanted the grid to have reliable, high quality power, stable frequency and voltage, and you want to also minimize the energy that you're consuming from the microgrid, which is not renewable. So you want to use maximum of those green energy sources, but you want to minimize the use of the microgrid. And so this is a whole, argumentation here that actually controlling such microgrid, because of the decentralized architecture, requires to make decisions at various levels. So to give you an example, a decision that I call a decision on micro scale, so on scale of a single household. So here we have the example of a household which has a battery cells and the electric vehicle. At any time, the people in this household can decide whether to charge their batteries when they're producing energy with their photovoltaic panel, or to charge their electric vehicle, or to trade this energy to the grid. And what is interesting there is that most of those trading are bidirectional, and certainly what is the best decision at any time depends on various parameters. For example, how large is the capacity of the cell, how expensive is electricity at this moment, and also the policies. So if you decide that you're gonna only use electricity that do not produce carbon monoxide, for example, that is like a policy. It can either come from you, or maybe it comes from other instances like governments, or maybe on a city level even. Okay, so this is like the micro scale decision, and there are decisions that are to be taken at so rather like higher scale, so I call them micro scale decisions. So we still have the same decision from the point of view of the household, but we also have decisions from the point of view of the microgrid, how to dispatch the energy to the different parties, and also especially considering those different energy carrier at any time, what like energy transfer you're gonna do from one medium to another. And it's not only you, it's not only about this single microgrid, but the decision that you make in your microgrid certainly also depend on the decision that are made from the other microgrids you're connected to. Okay, and so with that said, so it's clear that it's challenging, and there are different decisions that are to be made. But in particular, I try to articulate this and like as a set of like more specific challenges. So one challenges is, so I start talking about this. Basically, how we're going to manage the energy in the grid to make sure that there are no surplus of deficit of electricity at any point. So are you going to decide to say, you have a specific situation that can arise? For example, it can be that at the moment there is no wind, there is no solar energy available, and yet the local industry plant requires a lot of power. So what you're going to do, are you going to transfer energy from hydrogen into electricity, or are you going to use a heat network or maybe mechanical network? And each of those transfer has like different, say, dynamics and different impact in how you're gonna like about how much energy you have in your system. And so it's like one of the major challenges, in my opinion, is that how do we decide at any time? So which transfer or exchange should we do? Another challenge, which I think is interesting, is about the expansion of those networks. So as I said, with the example of the electric vehicle, those electric vehicles need charging stations. And it's preferable to have a fast charging station, but they also require a lot of power when they are being used. And it's all the question about how to dispatch them in the grid. So where to put those storage units and those high loads units. Third challenge that I think is also very important is how do we recover from a major disturbance, maybe caused by a disaster, maybe like I don't know, a tornado or some other hurricane, breaks down some of those links in your microgrids. Basically, what is interesting is how you're gonna like prevent further damage to the grid, and how you're gonna like make sure you provide energy to everyone. And the last one, so the control. So how do we maintain the balance in this energy system in terms of stable voltage, stable frequency, especially when you consider that you have a very high share of renewable. I mentioned it a little bit before, like we have very low inertia. What this means is that if there is like a small imbalance in the network, it's going to have more impact than a system where we have higher inertia, because you have the rotating machinery that is usually embedded into like nuclear plant or in a gas power plant, helps to modulate the frequency in the network. Okay, so it should be clear from now that the different decisions that are involved are difficult to make, simply because also the space of the decisions, possible decision, is very large, and those decisions must be optimal in some way. So with respect to a specific goal, so for example, this policy that we don't want to use any energy that release carbon monoxide, that could be one possible goal, but there are different goals. Like for example, if you want to maximize the money you're making by selling your energies, that also can be like a possible goal. But so just the decision must be optimal in some way, and also it should be done in a timely manner, so basically in real time, because there is no time to react otherwise. And that's why we need to automatize those decisions, and that's what in turn we call automated decision making. So from the point of view of like system engineers, so for example, electrical engineers, this is how automated decisions are made. So is there very traditional control theory, where you simply measure the difference between the reference and your measurement. So you measure the error from your sensors, and and you adapt the parameter of your system so that the error is reduced. So this is a very well-known control theory. Or also decisions can be made by humans. So here I've put a picture. This is like this control room of the European Space Agency. And you see, okay, you have a bunch of humans sitting in front of many many screens and with various indicators. And obviously, this kind of decisions first is not scalable. We can do this for one specific system, but we cannot possibly do this for a very large system or a numerous independent system. And yeah, also humans are also error prone in terms of decision making. So recent development, when I mean recent, I mean for the past 2 decades, I've seen major advancement in sequential decision making. And I would say, I mean, basically there are like two trends currently in the literature, at least from my point of view. Please feel free to tell me if you see others. But right now, okay, we have a lot of contribution in the area of reinforcement learning. So basically, you want to model this environment as a set of states, and you learn a transition matrix and the associated actions so that you can be in those states that are associated with high reward. And there are a lot of success stories with great empirical success. Unfortunately, as far as I can tell, we have relatively low theoretical understanding and or like low, say, guarantees that it actually work. And the other trend, which I find also very, very interesting, which can be seen as like a canonical formulation of the reinforcement learning problem, is the multi-arm bandit, which captures then this really intrinsic trade-off between exploration and exploitation. On one side, we have much more theoretical understanding, and there are a lot of things happening now. But at the same time, I would say the current model still struggle with respect to the characteristic of the real world. Okay, I don't know. There is a last one now. Okay. Now that there is a, no, it's good. Okay, so I just continue right now. There is a little bit of last sensor now. Okay, now it's good. Okay, all right. Yeah, I continue. So I mean, basically, I'm assuming that most of you are familiar with the multi-arm bandit problem, but so basically this is just a trade-off of like imagine the gambler entering the casino, and they want to find the machine that will provide them with the highest expected reward. Yeah, they are always like dealing with the trade-off. Should they play the machine they believe is the best so far, or should they explore and try another machine that maybe has highest expected reward? So that what I was saying is that unfortunately it's not enough when we consider the challenges of real-world systems like energy systems. In particular, I've articulated four specific challenges which I think need to be fulfilled before we can actually deploy this to the real world. First challenge to be dealt with, and I've already started with this, is dealing with concept drift. With concept drift, we simply mean, okay, that the distribution of data is subject to change in a way that cannot be, that is unforeseeable. And the second one is the uncertainty, because in many times, like, okay, we hear great success of like in machine learning techniques, but they often rely on a very large number of observation. And here it's different. We have actually a rather low number of observation, and the reason also partially because in the real world there are a lot of also privacy issues. Like, for example, we can't assume everyone would be okay with disclosing the current state of their batteries, and that is like information that would actually someone might need in order to make informed decisions. So the real world has much more uncertainties that, say, like theoretical settings, and also the decisions, they must be interpretable in a way that we could explain why we are making this decision and not this decision. Otherwise, there is no chance that people actually responsible for the grid are going to trust the decisions that are made by the system. And the last, but also very, I think, very interesting aspect is that it's not only one agent, it's multiple agents. So we have multiple grids which are interacting with each other, and there is no one single entity that say makes a decision for everyone. And so when you make the decision, you have to consider the actions of others. And I think there are even like, I have not developed this now, but I think there are even like interesting, say, game theoretic trade-offs that can be dealt with at this stage. And so it's been already identified in the literature, at least in our like machine learning communities, that those challenges are not being addressed enough, because those decisions must ideally be optimal and timely, and we are like nowhere close to this with respect to those the complexities of real-world systems. So that's a bit the vision that I see for myself as a young scientist. I would like to bridge the gap between this automated decision-making technologies that exist and those that do not exist yet, and the reality. And how I would do that, I would try to systematically address those 4 challenges of energy systems that I've just described, as well by considering also the complexities of real-world system. So on the one side, there is contribution to automated decision-making, and the other side, contribution to the future energy system. And the goal would be to like systematically try to address the intersection of each of those blocks in this matrix. So about the previous work of mine, so I became interested already during my PhD on the sequential decision-making problem. In particular, together with Genpei, we look at the problem of the multi-arm bandit problem with a variable number of plays. And now recently we also have an article on the archive, which is right now under review, where we actually extended this to the non-stationary setting. I will talk a little bit about that shortly after. And recently I had a grant that was accepted by the Baden-Württemberg Stiftung, so more like a local grant to the Baden-Württemberg area in Germany. Actually a fellowship where I actually want to continue explore sequential decision making for the noise discovery in data streams. So the project I just started, but yes, it's I kind of try to lay the foundation for this big goal. I also have several contribution on anomaly detection or outlier detection, as we call it, which I think certainly could be also relevant in this setting, although in a rather indirect way. And I've applied a few times during my PhD data science to energy data from a point of view of data reduction or estimating dependency, because I was a member of this energy status data researching group at KIT. So what I did during this time, and I became interested into the multi-arm bandit problem, I started from this real-world case study at KIT Campus North. We have an experimental power plant, the so-called BioLiq plant, that BioLiq stands for biomass to liquids. Basically, this is a pyrolysis process in which we try to transform biomass into biogas. And typically, us in like a data mining community, we say the data that is being produced on this plant is a high-dimensional data stream. So high-dimensional depends a little bit from one community to another. What is a high-dimensional? Some people say it's 5, some people say it's 10, some people say it's 100. In that case, this plant was instrumented with about 800 sensors and producing 1 new data point per second. And the people we were talking with, which were like designing this process, were interested in this, throughout this process, how does like the dependency between various like physical measurements of temperature, pressure, etc., are correlated with each other throughout the different steps of this process. So, so this look like, from our point of view, this look like a monitoring problem. So how can we say efficiently monitor the correlation, or how the correlation changes in this data stream over time? And that's so okay. This like okay. The naive way would be to take any measure of correlation or dependency. I mean, it doesn't have to be linear correlation; it can be nonlinear correlation. And the naive idea would be to simply recompute correlation matrix between every pair at any time step. But the idea is that okay, especially if you're considering even like dependency between more than two sensors, we have an incredibly large number of pairs, or incredibly large number of subsets. And it turns out that, and that was like say what came up from the discussion with people, that many of those pairs are not interesting. Say, okay, the correlation is very low, or maybe it never changes. And so if it never changes, then it's worthless to recompute at every time step again. Okay, what is the correlation between this pair? And so that's what I wanted to investigate. Can we reduce the cost of monitoring if instead we find what are those interesting pairs over time? Now the question is like, okay, which of those pairs in this correlation matrix are interesting, and how many of them actually do we need to recompute on a regular basis? And that's when I had the idea to model this problem as a multi-arm bandit problem. So again, imagine you're in the casino and you're facing a set K of bandits or machines, and you want to know in which of those machines you want to place a coin. But so you want to maximize your gain at the end of the day. You want to find those machines with highest, say, expected reward, which you don't know a priori. You need to estimate it from your observation. And I found that what was different from the existing contributions is that we are okay. So like, and also there's one more difficulty to this, is that the expectation of those machines may also change all the time, and in ways that you cannot really predict. So you need to adapt. And so what I found was different from the existing, say, bandit approach from the literature is that you don't only want to know, okay, which arms are the best, but you also want to know how many of them you should play. And you also want to know when you should adapt in the face of change. So yeah, here I put again, imagine this is an example with this correlation matrix. Here it turns out, okay, like there are like five of those pairs which have high correlation, and this are interesting, and you want to find which of them there are, and you want to find whenever they change. So this is just a construction of the classical multi-arm bandit problem. So we have k arms, and you assume that the reward of each arms follow a Bernoulli distribution with a specific mean, and at each round you choose one of the arm, you observe a reward that is drawn from the corresponding distribution, and based on this observation, you update your estimation of the mean. In the end, what you want to do is you want to maximize your gain. So you want to maximize the sum of those rewards that you get. And now that's
so
yes.
Then the probability of the Bernoulli distribution is different for each one of the k arms.
Yes. So it is of course, like it's different, and some of them. So to take our specific setting, the assumption is many of them the mean is very low. And some of them are high mean, and you want to find them. But yeah, I mean, if they were the same, then playing any arms would be the same value and expectation. Yeah. So they have different means. And so this is like the classical formulation of the multi-arm bandit, and there are a lot of work and there are a lot of algorithms that actually are able to find those arms with the best mean in logarithmic time, which is great. But so our formulation is slightly different in a way that I mean, we call it the scaling multi-arm bandit because here the number of plays that you do over time scales. So basically what you want to do, we formulate this as a constraint optimization problem. You want to maximize the sum of the rewards that you get. So you want to find the set of arms whose sum of the reward over time is maximal, such that still the average of your reward is greater than some threshold, which we call efficiency threshold. So basically what this means is that you can play a different number of arms, but you want an expectation from those arms that you play that at least a certain portion of them are like successful, like they bring you one. And so what we found is that basically, if we assume that the player always choose the best arms, so those with the best means, then the problem is actually equivalent to finding an optimal number of play L star, which is the largest number of play, such that the efficiency threshold that is here is still fulfilled. And what is nice is that we still have, we already have like techniques that allow us to find the best arms. And now that we have formulated this, we just need the missing part that let us find the optimal number of play quickly and reliably. And so that's what we did, like basically a sketch of the algorithm right now. So it has basically two components, which is just finding the top arms. As I said, it's like existing Bandit algorithm already solves this. So you can be UCB, Thompson sampling, or basically any kind of Bandit algorithm that can find the best arms in logarithmic time. Plus a part that is new, which is a part where we want to find the optimal number of play. And so what you do in this algorithm is at each round, you choose a set of arms. So it's a multiple play, multi-arm bandit. You choose a set of arms, you observe a reward vector. So you get one reward for each of the arms that you play. And then you update your estimation of the mean for those arms. And then you choose the next number of play you're gonna do. So at the beginning, I mean, in our algorithm, basically we start with you play all the arms, and basically you shrink the number of arms until you're confident that you don't need to shrink anymore. And so there exist multiple approach, as I said, for step one. So for example, multiple play Thompson sampling, which is basically previous work also from my colleague Junpei, and also upper confidence bound type bandits, which are also very well known. And for the step three, so this is like this part that is new, we introduce what we call a scaling policy. And so on the next slide, this is our scaling policy. So every time we call it Kullback-Leibler scaling because it is based on an upper bound that is based on Kullback-Leibler divergence. At each round, we play a set of arms and we ask the question whether the current play is below the efficiency threshold. So that's a yes/no question. You just check whether you fulfill the efficiency threshold. If that is the case, no. Okay, yes. No, the question here is the other way around. We do not. We want this, sorry, this n here to be greater than the eta star. So here, in that case, it is lower. So we do not fulfill the efficiency threshold. In that case, we should scale down. So instead, we should play one less arm at the next round. If that's the case, that say we fulfill the efficiency threshold, we would like to know whether we are confident that we will satisfy the efficiency threshold if we play one more arm. And if we play, so if we are confident, and this is an upper bound that we compute with the Kullback-Leibler divergence, then we scale up. So we play one more arm. And if that's not the case, then we just keep the scale. And eventually, we're going to converge to the correct scaling. So how do we evaluate this in the end? We need to make a distinction between, okay, we are finding the best arms, and are we likely to find them, and we are finding the optimal number of play. So those are two different things. And in traditional Bandit algorithm, you use regret, which is simply, okay, the difference between what is the expectation of the best arms and the expectations of the arms that you actually play or actually think are the best. So this is a standard regret from the Bandit literature, and then we introduce a simple additional regret that we call the pool regret, which is simply the absolute difference between the optimal number of play and the actual number of plays that you're doing. So intuitively, if the standard regret is small, it means that we have found the top L arms. And if the pool regret is small, it means that we have converged to the optimal number of play. And so here, that's where I don't go more in detail, but we actually prove in our paper that the regret and the pool regret are in logarithm with time, thanks to the scaling policy that I just described before. And then this only works, of course, for the static setting. So you assume those means and those this optimal number of play does not change over time, always the same. And since in our case with the biotic plant, actually it was a rather like highly non-stationary setting, we thought, okay, we need to find a solution that would also work if that changes. And we had an idea, which was to combine the scaling multi-arm bandit with adaptive windowing technology. So I don't know if you know it, it's an algorithm known as AdWin. Was invented in 2007 by Albert Biffet, who is, I think he's a professor at Telecom Paris Tech. But basically the algorithm is really simple. Like, well, the idea is that you have a sliding window. And so here is a sliding window. And basically at any time, you ask for any two sub-windows whether the mean are significantly different or not. And if they are significantly different, then you would cut the window. So, and if they are not, like if there is no window where the observation is significantly different, you would grow the window indefinitely. So that is nice, because if we let the window grow and it's indeed stationary, then we're gonna increase our confidence in the system. But if there is a change, then we cut, and basically we are controlling that way. We are able to go back to like again exploration. It's because traditionally we always start with exploration, and in the end we never explore anymore. We only exploit. But here with AdWin, you have a resetting mechanism that allow you to go back to exploration. And what we found at this stage is that when we do combine them, we have very good empirical performance. And that's the time where I met also Paul in Japan. We had this thing, and we were also wondering, okay, how are we going to show that we are going to actually have very good performance also in theory? And we didn't know, but that's what we talk about in our recent preprint. And I still say a few words about that after. What I wanted to show here is just some empirical result that we did on this biotic power plant. So simply we just took 20 sensors, so a very small set of sensors, and 1 week of data. And what we found is that so there is like, it's 1 week of data, and what is interesting is that you can see there is much less activity at the end and the beginning of the week, because this is the weekend, and so the plant is not being in operation. But then after the plant is in operation, and there is a lot of say activity and a different correlation. And what we found, so here is like the number of play, and here is the efficiency. What we can see is that, okay, at the beginning we are far from this like efficiency threshold, but as the system learns, we tend to stabilize around this like optimal efficiency threshold. And what we found already when we were looking at this curve and we put it into numbers is that our combination. So the oracle here is like basically always selecting the best arms of the while here we have the scaling which Bandit and the scaling which Bandit combined with Edwin. What we found is that after some time, the scaling which Bandit combined with Edwin would follow very closely what the oracle does. So yes.
What is the frequency of the data?
It's just 1 point per second. So it's,
1 point, so it's 1 second.
yeah, yeah.
Okay.
So there are not so many observations because just 1 week. So it's like yeah, 60 times 60 times 24 times 7 points. So it's not so many points actually. And so that's when we continue the work, and we wanted to know, okay, why is that it works so well? And we were looking at this because this is another view on the same data. So this 1 week data from Biolic. We are looking here basically. Here's the different, on the y-axis the pairs, here's the time. And basically you see a dark square where the mutual information between two sensors, so a pair, is greater than 2. So which is, we say, okay, this is like large dependency, or at least large enough, but we have to set the threshold somewhere. And what we found is that when we look at it, we found that in the plant, there are a group of arms that tend to change together. So as you can see, okay, not much happening here, but basically there are some like discrete time step where you can see like things have changed massively from one step to another. And so our idea was like, okay, maybe we can assume that the change are global in some way. And if we can do that, maybe we can prove that the scaling multi-Bandit Edwin has the best regret also in the stationary and the non-stationary setting. And actually, that's what we did. And I mean, it's current work. It's under review. Maybe we can talk about that another time. But what I want to show lastly is I actually have applied this technology in other settings. So in the setting of outlet detection, I just want to show how it can be useful as well beyond. So yeah, monitoring to knowledge discovery. There is a world trend in the data mining community, which is about subspace search. The idea is that not all subspace in the data are equally interesting. So subspace are likely to reveal patterns, so clusters or outliers, while others are just like, okay, look like randomly distributed. And so this is here the example. So you have subspace 1 to a specific dimension, which are like completely randomly distributed, and you have some other subspace where clusters or outlier can be shown. And the idea with the subspace search is say, okay, those subspaces which are interesting tend to have higher dependency, and so we want to find them. It's difficult because there is an exponential number of subspaces in the data, and there have been in the past, okay, like really improvement in terms of like people looking for patterns in the data with subspace search, but there was actually very little work for subspace search in data streams, so from data that is changing dynamically. So okay, there are so many subspaces, and the interesting subspaces may also change over time. And that's what I proposed in the end. At the end of my thesis, I proposed a technique which basically put it all together. So I don't know how much in detail I should go on this, but basically the idea is that you have some initial subspace search on the first window of data that you have, which deliver you a set of subspaces, so one subspace per dimension. And then the idea is that you monitor the dependency within those subspaces based on the sliding window. So you want to do this efficiently, and okay, there are like some algorithm to make this efficiently so that it's manageable with your computer or your server, whatever. And then I employed those like scaling multi-Bandit in order to find out which of those subspaces needed to be replaced, which of them are changed. And when we take those subspaces at any time and we put them into any like data mining algorithms, so there are a lot of algorithms for this clustering or outlet detection. The idea is that the knowledge that is out of this, because we are applying on the subspaces and not on the full space, is of greater value. And I just, okay, here, it's not super interesting. It's just a table with some number, but basically we did some benchmark on outlier detection. And what we found is that we could achieve much better outlier detection with this technique compared to other methods. We try to do outlier detection in data streams. Okay.
What are the columns?
The columns, so we have basically this is an area under the curve. This is the average precision. This is average precision. This is the precision at the top 1%. I mean, those outlier detection basically return you a ranking of outliers.
So our evaluation of the different algorithms.
Yeah, I mean, those are the algorithms here. Those are different data sets. And those are like just different measures. So this is precisions and this is recall.
Okay. So each one of the three is like an electricity network.
And in that case, it's not electricity network. It's actually just like accepted benchmark in the community that we use for comparison.
So which type of data are, for instance, activity and KDD group?
For example, KDD cup was a challenges that was posed in 1999, so it's a bit old already.
Okay.
But for network intrusion in network data.
Okay.
And activity, I think it was more like human body activity recognition data set.
This type of data stream.
Different data sets that can be seen as data stream.
So we don't have again an application of data stream in electricity.
No,
network.
we don't have it. It's not. I mean, it was this specific work was about the technique itself and not so much about the electricity network. But I think in the future it would be very interesting to also deploy it there. Yeah. And so actually I would come to my conclusion. So I think it's obvious from the structure of the talks that if we want to approach this, we need to work in a way that is interdisciplinary because I mean, I'm a computer scientist, I'm not an electrical engineer. So we do need to team up with electrical engineers. And it turns out that at KIT we have some really interesting groups that are working on that. In particular, right now I've set up a collaboration with Dr. Descarnes, who has his own group at the KIT. He's investigating exactly this interface between different layers of energy network. And this is again the big picture that we had in the first slide, with basically this like experimental plant at KIT where they basically engineer those processes. So that's the idea right now, and I hope I'll be able to do that in the next years. But I mean, it's work in progress. I'm still refining this vision, and I hope maybe we can have some interesting discussion about that. Yeah, just my conclusion. So two problems: those future energy systems are going to be very difficult to manage, and on the other hand, the existing technique for automated decision making cannot cope with such complexity. The solution is interdisciplinary, and I just talked about some work about multi-arm bandit, extending multi-arm bandit problem. So that's it from my side, and okay, here are the reference, and that's it. So I hope maybe you have some question either right now or maybe we can even talk offline. You can always contact me. Thank you.
Thank you very much. I don't know if one can hear me. So thank you. Are there questions or comments?
Please, we do not hear anything.
Are there other questions from the others which are online now?
I hope they could hear me.
Yes, I think so. I think so. Okay. Else, I would like to thank you again, and I will just stop the recording, but we can go on speaking maybe in French. I don't know. So thank you very much.